Thanks to Tim Ventura for giving the invite for this talk. Today, I am going to discuss antigravity in the most general theory of relativity, and I'll talk about what I mean by that. And so I got a PhD in theoretical physics, and now I work at quantum gravity research. So I was asked to talk about antigravity and simplify it for the level of engineers. So I thought about what that meant, and I thought about it in this term. So if you think about what an engineer is, we have mechanical engineers. They often study Newtonian mechanics and have to learn a lot about stress and strain. We have electrical engineers. They learn about Maxwell's equations and circuit theory. Material science, they are engineers and they need to learn some quantum physics. So aerospace engineers, they really need to learn all of the above. So they need to know mechanical, electrical, a little bit of material science, fluid dynamics, hydrodynamics, thermodynamics. So if we're talking about being serious about antigravity and we want to simplify it for engineers, what that means is we need to be able to teach quantum mechanics and general relativity to engineers. So that is what I'm going to try to do today. So just to provide a little bit of background about myself. So I mainly study quantum field theory and general relativity. And quantum field theory is the most successful theory for describing all of the forces of nature, quote unquote, besides gravity, but it's actually not as problematic as people say. So it's very successful for electromagnetism, quantum electrodynamics, and also for adding in special relativity. And some of the biggest experiments on the globe right now were the LHC, where they detected the Higgs boson. It obviously got a lot of news, a lot of money went into that. And then general relativity is the other big theory of gravity, and people are figuring out how to quantize it right now. And basically, LIGO is the other biggest experiment in the world, and they recently have detected gravitational waves. So I got a degree in undergrad in physics at MIT, and when I was applying to grad schools, I wanted to use Feynman diagrams from quantum field theory to calculate general relativity. That's what I said I wanted to do when I applied to grad schools, and everyone told me I was naive, but I got into one school because there was a professor there who had already computed these things, and I didn't even realize that people had already done this, but most people in the field didn't realize this, and he was able to calculate gravity from the other forces of nature, the strong force. So that's very curious. Basically, what is the most general theory of relativity? Well, we know that general relativity uses Riemann curvature for its framework to describe curved spacetime, but the most general mathematics for general relativity or gravity in general, this differential geometry, there are more exotic types of geometry, and a lot of these are necessary for quantum gravity. And this includes concepts like torsion coming from Cartan and non-metricity coming from Weil and others. And basically, spinors are used to describe matter. And in order to get angular momentum conservation, we need the torsion. And some of these unified field theories right now are using non-metricity. So it's pretty exotic stuff, but we don't need to know all the details of this. But I want to mention this because there are some interesting aspects of this theory that are contained, that have effects related to antigravity that are not in general relativity, that are related to some of the things that people in this area are discussing. So I figured it'd be worth mentioning that. So I want to take a very conservative approach to antigravity. I want to be serious about it. I want to bring some respect to this conversation. I mean, we have to be very serious when we're talking about doing this because it is very challenging. So if we're going to think about metric gravitational engineering, we have to understand gravitational theory, and we have to be able to work with it and understand how antigravity is coming out of it. Realistically, we're going to use electromagnetic devices made out of materials, and we're probably going to want to induce some quantum behavior in those materials in order to get the effects we want. Therefore, we're going to have to understand how quantum materials interact with gravity. And I think the best way to do that is to understand how quantum gravity works. That way you understand unified field theory. And if we can understand unified field theory and can look at how Maxwell's equations and general relativity play with, if we know that we have a unified field theory that is decent enough, then we can at least have some confidence in the theoretical framework that we're working with. If we're not even sure what quantum gravity is and we're taking quantum electrodynamics and adding in the gravity, and we don't know how those play together, we might run into problems. So my goal today is not to suggest the best way to do it necessarily. I just want to provide evidence to motivate further study of it from this perspective of unified field theory. And I just want to mention, for the sake of humanity, this analysis I'm going to present was only really possible by making friends of enemies. So I've been looking at a lot of different theories and a lot of different people's work, and a lot of times what I try to do is figure out, if there's two people that disagree, what is the underlying framework where everyone can agree and be happy. And so I'm going to show you that perspective today. So just to give you a little possible timeline about how maybe things could work, right? Maybe in the next decade, there's going to be significant progress in understanding quantum gravity and unification. Who knows? Maybe there could be some legitimate textbook that's actually written on how to combine quantum mechanics with gravity to do something like metric engineering for these types of applications. You know, who knows where that'll lead? Question mark. But maybe it'll lead to profit in the future. And I just want to mention that, you know, there's this idea of the Jetsons. They came out in the 60s, and they had this 100-year projection in the future. So we're about halfway there. And so I just asked you guys, does it feel like we're halfway there with the technology? Something to keep in mind. So in nature, I guess I tried to pick the least controversial things that I could find that are helpful for trying to understand antigravity. One of them is dark energy, because we find that galaxies are pushed apart and it's a gravitational effect. So it seems like that is a natural type of antigravity. Obviously, that's not practical for engineering, but it's worth to try to understand that in the framework of general relativity, just to understand how something like this might work. Also, there's this notion of torsion and very high spin densities, creating essentially a finite size for particles. And there's also the connections here to topological field theory. And so it's sort of a type of antigravitic effect. And so I think there is also this sort of analogy that you can make between this and the metamaterial effects. It's a little vague analogy, but I figured it's worthwhile to mention, just because it is deep physics that is important for trying to understand quantum gravity. So the third topic I'm going to mention at the end is this idea of pumped metamaterials. Mainly, I'm going to present ideas from Jack Sarfati that I've just seen from email threads. And it just seems like he seems to be the only person I've seen that realistically is addressing the theoretical problems necessary to make something realistic. It's definitely a work in progress, and he's far away from having something realizable, but he is working with a theory that actually provides some hope for something to work out. So if we're going to get into this antigravity stuff, we need to know the basics of general relativity. So the first concept in special relativity is the unification of space and time into space-time. So we have these Lorentzian four vectors where time is given this kind of, it's almost like an imaginary dimension, such that when we measure the distance in flat space-time, the time adds this negative effect where space is has a positive length. And then in general, for general relativity, we have curved space-time. So there's this more general space-time metric, g mu nu. And here I just depicted this idea of having foliations of space-time, and you could imagine being a particle traveling along a path, let's say in the z direction, and at each moment in time, you have two dimensions that are transverse to your direction of motion. So, and you can have curved space-time in general relativity, and that describes what gravity is. So basically what ends up happening is you have derivatives, there's calculus involved in, obviously, and the derivative gets enhanced to what's known as a covariant derivative, and this also occurs in electromagnetism, so that's curious. And the covariant derivative involves this connection, and this connection affects geodesic motion and provides a fictitious force to describe acceleration. And this is the variable that goes into the curvature. I didn't even write down the exact formula for curvature, but the connection goes into the curvature. And so you can think of the connection as being sort of the potential and the curvature being a field strength. And so we have these different types of curvature. There's this 4 tensor because there's 4 space-time Lorentz indices here, but we can contract these indices. So we get this Ricci 2 tensor. and we can further contract to get this Ricci scalar, and Einstein's field equations combine the two tensor and the scalar with the metric into this field equation where we have the curvature on the left-hand side of the equation and energy, momentum, and stress and strain. The energy momentum tensor is on the right-hand side. So this is going to be all the sources of gravitation, whether it be matter, electromagnetism. And what we're going to focus on at the end of the talk is the coupling between energy, momentum, and curvature, this 8 pi g over c to the fourth. So keep that constant in mind because we really need to get over this barrier. That is the biggest problem, is understanding, let's say we had negative energy somehow. That's not even the biggest problem. The biggest problem is getting over this hurdle, which is what Jack Sarfati has really been addressing. Sorry, I meant to add some drawings here, but I didn't have time to get there. So why is anti-gravity so hard? Well, basically, we can look at this coupling constant here between matter and curvature, and it's astronomically small. I mean, Newton's gravitational constant is pretty small. And then we have a speed of light, which is pretty big, but that's in the denominator. And then we have it to the fourth power. So we have this huge number in the denominator to the fourth power multiplied by this other small number, giving this extremely small number. So even if we can find negative energy, we're going to need a lot of it to curve space-time enough to have an actual effect. So if we're just tinkering around in our garage, or if we're an engineer without knowledge of general relativity, I mean, you can hope that maybe you're going to get maybe 3 orders of magnitude. I mean, that would be amazing. You know, getting an order of magnitude in increased strength is a big deal. So if we're going to have to get it over numbers like 10 to the minus 43, then we really need to know what we're doing. So what is meant by anti-gravity? This is also important to talk about. I don't mean something like magnetic levitation. What we mean is this antigravitic effect would affect light and heavy objects proportionally, because, you know, if you think about a rocket, you're going to use jet fuel. If you have more mass, you're going to need more rocket fuel. So the same sort of limitation occurs with magnetic levitation. So that's why it's not true anti-gravity. So we need to understand what types of matter lead to efficient solutions such that we can control the curvature of space-time itself to get these effects that we want. And metamaterials are probably the best candidate, because metamaterials is just a blank term for exotic materials that have bizarre properties. And to understand how to do this, we really need to understand how electrodynamics and gravity come together. So I'm briefly going to go through unified field theory and particle physics. Honestly, most engineers don't need to know the details of this, but I really do think that the people who are figuring out how to bridge the gap between the science and engineering are going to need to understand some deep stuff that are at this level of difficulty. But I'm going to try to dumb it down for everyone. So we can think of types of anti-gravitational fields just in general that might occur in our universe. And we can see that there's the creation of matter via extremal black holes in supergravity and string theory. And we're understanding how black holes are basically fundamental particles. And the particles, there's this notion of renormalization where the particles actually get an effective size. So we have these point particles, but really we have to realize that they have some finite volume. So you can think of that process as sort of being an antigravitic effect that pushes things away to give it that finite size. I find that a little bit helpful. Obviously, this isn't practical, but it's important to understand how this works, in my opinion. And also looking at cosmology, such as the expanding universe, this relates to the dark energy and how galaxies expand. So, I mean, if we have the theoretical understanding to address quantum gravity and these types of effect of, you know, extremal black holes and cosmology, if we have that theoretical framework and it's there and we can apply it to reality, then I think we might be ready to start opening the dialogue for how could we, you know, get realistic anti-gravity effects. So at the end, I'm going to try to get more realistic and talk about this idea of pumped metamaterials. And so basically for a unified field theory, the idea is that matter is sort of made of the same stuff as space-time. You have this unified field where everything is the same object. And so as I was saying, you could think of point-like singularities actually occupying some volume after you consider everything that's going on. So even if you don't study torsion, the topological field theory community also finds the same effects, but these are actually two sides of the same coin. So I say this to say that there's differing opinions where people are studying different fields, but when you stand up above them all and see how they're connected, they're pointing in the same direction. So this is kind of what I'm talking about, where enemies, someone might study topological field theory and not care about torsion and not like that stuff, but they really actually do point to the same direction at the end of the day. So matter is creating these regions of isolation or these voids within space-time itself. And this actually is relevant for thinking about how string theory and extra dimensions work, because we actually think of the entire space-time as this type of brane world, which is essentially a material which is embedded in higher dimensions. So you can think of a fundamental particle as getting an excitation, and from our perspective, it's just a point, but really there's some volume. So you could kind of think of the extra dimensions as being the topological information that is filling that void. That's one way to think about it. So I'm going to spotlight a few respectable scientists in this talk. One of them is Joel Shirk, because he was the co-inventor of string theory and supergravity, and he was the one who realized that string theory was a theory of quantum gravity. So I also mention this because he wrote a paper on antigravity a few months before he died, based on a tragic accident. But basically, supergravity, with this notion of extended supersymmetry, has antigravity. It's a fact. And if supersymmetry does exist, you could be skeptical. Is this should we even care about supersymmetry? The point is, even in order for supersymmetry to work, we need extended supersymmetry. So extended supersymmetry is what has antigravity. So not all supergravity theories have antigravity, but the ones that are realistic have antigravity. So that is interesting and it's curious. So maybe we should listen to what these experts in the field are saying. So I'm going to briefly bring you through the evolution of string theory very quickly. So it started off with 0-dimensional points in 4 dimensions. They did some mathematics and realized that there are these nice superstrings that could exist in 10 dimensions. There are these 1-dimensional objects. And so they changed the particles of strings, and then they changed their mind and they said, well, actually there's supergravity in 11 dimensions. And Ed Witten realized there's this M theory that unifies string theory and supergravity together. And there they use these 2-dimensional membranes that generalize the string. So they're getting away from the point, they're getting away from the string, and now they're going to these membranes. And the story doesn't end there. Really what happens is there is this larger theory above M theory. There's a few different ones, and these are making contact with this 3-dimensional brain membrane, same thing. And there are these notions of F theory, S theory, and recently A theory in 12, 13, and 14 dimensions. And what is a 3-brane? What are we talking about? What are all these complicated stuff? Fancy way to say it's a material. I mean, it's this 3-dimensional object that fills up a volume, and it occupies 3 dimensions of space, and it's lifted to extra dimensions. So these extra dimensions, it's very simply just internal spaces for charge and associated with other forces. So space-time is associated with gravity. We have other forces, and we need to describe the conservation laws for energy momentum as well as the other charges. And those extra dimensions are just there to allow for this unified conservation law. It's that simple. We don't have to get all mystical about what these extra dimensions are. So type 2b supergravity has this 3-brane, and M theory actually doesn't make contact with it. It's a little convoluted. It's claimed that M theory unifies all the supergravities, all the string theories, but when you actually study it, it's a little convoluted the way it's connected. There's these chains of dualities. So the superalgebra of M theory doesn't actually contain all the supergravity superalgebras. And the physically realistic ones involve this 3-brane. And so really getting back to this idea of something like an ether, I mean, they're just saying that there's this material. And so it's not that new of a concept. So just to establish myself. So in 1997, this 14-dimensional idea was put out by Ishtek Bars, who's a very serious string theorist. And no one is really, this isn't really something you're going to hear from many people in mainstream media, because no one's talking about it. I mean, it has a few citations, but in the past decade, really only me and my collaborators have cited this work. So not even the string theorists who are bad at communicating with the public are talking about this. So the chances of anyone hearing about this are very slim. But I'm going to make it really simple for you guys. So we're in 14 dimensions. How do we describe this if we're in kindergartner? So I'm just going to use addition multiplication, and I'm going to divide by 2 at the end. So I hope the engineers can keep up with me here. So this theory has 11 spatial dimensions, space-like dimensions, and 3 time-like dimensions. And you follow through the symmetry breaking, and you realize that you can break off 8 spatial dimensions into 3 plus 8. And then the 3 time dimensions, it's not that mystical or complicated either. It's just one time dimension with rotation angles for mass flavor oscillations. So in the standard model and beyond the standard model, we know that there's 3 mass generations of particles, like the electron, muon, and tau families. And I figured out how this is related to the 3 time dimensions. And basically, the 8 dimensions here are related to the 8 charge configurations. And basically, if you're an electrical engineer, maybe you've heard of a Fourier transform. Momentum and energy is conjugate to space and time. And we know that equals mc squared. So that helps understand why the extra time dimensions are related to 3 mass generations. And basically, charge is conjugate to this gauge degrees of freedom, these extra spatial dimensions, such that we see that really these extra dimensions are just for this unified conservation law of energy, momentum, and charge. So when we look at this theory and you study the spinors of it and you look what matter is involved, you get these 8 charges with 3 different mass states. Okay, 8 times 3 is 24. All right, we can do that math. And then if you look at the particle content, there's proportionally, there's 3 quarks for 1 lepton, because you can have a red, green, and blue quark, but those red, green, and blue quarks have the same mass. So for 4 particles, there's 2 mass values, and the 24 divided by 12, 24 divided by 2 gives you 12, and there's 12 different masses associated with the standard model fermions depicted here. So see, this is string theory. Really, this is where it's going. It's connected to the standard model. I did not introduce any unphysical superparticles. This is reality and nothing more. So here we go, right? So now that we've established the unified field theory, we have quantum gravity. We can now talk about, we can get into the engineering a little bit, but really just remember that we want that simple picture. And basically what happened is Lisi's E8 theory, when appropriately formulated, is really essentially related to appropriate formulation of Witten's M theory, because Witten said M theory is an E8 gauge theory. So we had to make enemies friends here, because Gerrit Lisi was vague, but he was trying to get some simplicity, and string theorists used E8 a lot, but they missed the simplest picture. All right, so now to try to get into antigravity, we have these fundamental particles as extremal black holes. And basically, in order to get angular momentum conservation, they need to have torsion inside matter. No one can get away from this. Everyone tries to hide it. They try to get rid of the torsion, but it has to be there. It's undeniable. Even the supergravity people have it. Even the string theorists have it. And it is essentially an antigravitic field. And this is not a perfect analogy, but you can think of the high spin density that sources this antigravitic field as being somewhat analogous to this high frequency pumping in these metamaterials. It's a completely different effect, obviously, but just keep that in mind. Just something to bridge the gap. So, and just to remind you what these extremal black holes are, basically, if you have some black hole, it can Hawking radiate, but there are these low, after it radiates all its energy, it reaches some excited state that it can no longer radiate. And those are extremal. And these extremal black holes are essentially fundamental particles. So we have a decent understanding of this. And I figured I would just spotlight another scientist. I meant to grab his picture, Nikodem Poplawski, because he figured out how to use torsional regularization, and he applied it to QED. And this really helps provide the philosophy for quantum field theory making sense, because he showed that it only requires a finite amount of energy to create an electron. And this has been a problem for decades. So since he's in the gravitational community, not many people have seen this work yet, and it's very difficult mathematics, so he hasn't extended it to gravity. But if this was extended into gravity, it's conjectured that this would help provide UV finite quantum gravity. There's other things that would be needed as well, but there's progress in that direction. So think of this Cartan radius as being the size that, the minimal size that the particle gets gravitationally from its own spin, that basically creates this antigravitic field that doesn't want anything to get close to it. You know, just, it's a little analogous, but we want to have something somewhat similar to that with these metamaterials. I mean, we want to get this craft that creates this bubble around it so nothing wants to come in, and that way it's very easy for us to sort of bend around gravitational waves, because the waves themselves would just bend around this object. Because to us, it would almost look like we're a point particle, so everything would just flow right through. I mean, that might not be literally what is happening, but I think it's the best analogy that we can get for, you know, some engineers today. So another person I want to just put on the spotlight is Hagen Kleinert, because he's done a lot of interesting work looking at Einstein-Cartan theory, which has this torsion, and he models space-time as a crystal just as an approximation. And he studies curvature as defects and as well as torsion. And so when you think about this perspective, I mean, it's once again suggesting that space-time itself is like a material, right? So to further motivate us to go into metamaterials, I'm trying to point out how, you know, quantum gravity is pointing at this idea that space-time is sort of like a material. And also going beyond the torsion, there's this notion of conformal gravity. This relates to cosmology and to try to get around singularities. So you want this idea of a geodesic completeness. There are kind of mathematical issues with general relativity, and going to string theory doesn't solve them. You need to use conformal gravity. So the string theorist studied conformal gravity as well and figured this out. And this will help with a lot of issues with cosmology. But they also have discussed antigravity in this theory. And this theory makes it easier for types of antigravitic effects. And a lot of people thought that this would be problematic due to issues of unitarity and causality, but they fix those problems. Okay, and this theory also is magnificent because you may have heard that the Higgs particle is this God particle, but it's definitely not the God particle. If there was such a thing, the Higgs is a false God particle because nobody is describing the origin of the Higgs mass itself. But this conformal gravity theory does that. So what it ends up doing is it turns all of these mass parameters. In conformal gravity, everything is massless. It has to be that way. But you get these scalar fields, and when you study how this scalar field condenses, when you basically symmetry break to low energies, the scalar field takes a constant value and it sets a mass. So it's a gravitational Higgs mechanism. And this is very elegant physics. And so it unifies the Higgs mass, the cosmological constant that is causing the expansion of the universe, and Newton's gravitational constant, all into this dynamical scalar field. And this is very similar to what Jack Sarfati is doing, because he's trying to add this scalar field to Newton's gravitational constant. So I say all this unified field theory stuff just to motivate Jack's work, because otherwise it might just seem like he's saying something crazy. So in this most general theory of relativity, we'll just go through a brief history. I wanted to mention Heaviside gravity just because a lot of these anti-gravity people, they like to talk about it, but they don't understand the mathematics of it, and they start saying dumb things. So basically, this Heaviside gravity used electrodynamics for gravitational theory, but it doesn't match experiment. Maybe there's a chance it'll work, but I don't think so. And people often point to Hefemenko as solving it. He implied he solved it. I bought his book, I read it, he did not solve it. So we can't just claim that Heaviside gravity is going to give us anti-gravity. We need to go to general relativity. But I want to point out that metric affine gravity contains general relativity with other forces that are equivalent to Heaviside gravity. So even if Heaviside gravity isn't the final gravitational theory, there is some partial truth to this, because it might turn out that this Heaviside gravity term is a gravitational field. However, it's realistically not feasible in experiment today because we still don't understand how it works. Maybe it's theoretical possible, but it's going to be a very weak effect, very, very weak. So we can't really rely on Heaviside gravity to get what we need. Just to talk about more legitimate scientists who have discussed interesting ideas such as space travel. Recently, there's a paper by Maldacena and collaborators where they're discussing this brain world idea, which is what I'm talking about, and they're embedding in higher dimensions. They're using this. He studies ADS CFT holography, and the CFT is conformal field theory. It ends up being related to this conformal gravity theory that I was talking about. And so he was able to get traversable wormholes, so he claims. And I mean, maybe it's a little interesting. I kind of looked at it very quickly and did some back of the envelope calculations. Maybe with what he was describing, maybe he could get like a half of a proton through this wormhole. It was going down 10 to the minus 18 meters is what it seemed like. And realistically, we can't even make experimental contact with that. So we're starting to get people who are thinking about these ideas and showing that it is legitimate, but we're still far away. Well, maybe not. Let's see though. Okay, so everyone talks about this Alcubierre drive because we can get this solution to Einstein's field equations that allows for high-speed travel. And the problem with it is it requires a lot of negative energy density. Okay, it's one thing to get the negative energy density, but how do you get enough of it, right? That's the big problem. No one is talking about it. Anyone who, they'll talk about Heaviside gravity or general relativity. I mean, you have to talk about general relativity here, but I mean, anyone who's talking about these solutions, they'll just make some vague statements and not do any of the mathematics to show how they're getting a strong enough effect. Okay, so we need to now talk about electrodynamics because we need to talk about materials. So Maxwell's treatise is prolific. Obviously, he introduced these electromagnetic fields. Well, he wasn't the one that introduced them, but he really fully understood them and how they all fit together. So he had this electric and magnetic field, and he also had this electromagnetic potential. He had 3 different variables that were all independent, and he had 3 types of energy. I read some of his work, from him himself, and he talks about these 3 types of energy. And today, this is called the macroscopic formulation. Shortly after, everyone was interpreting his work and simplified it. And they have the electric and magnetic field at this time. And then quantum mechanics came along, and then they said, no. The electric and magnetic fields aren't fundamental. It's the electromagnetic potential. So now today, we believe that the electric and magnetic fields are kind of this afterthought, and really this electromagnetic potential is fundamental. But I just want to remind you that Maxwell actually said that all 3 were fundamental. So maybe he was onto something. And so now when we get into macroscopic materials, I also want to mention that in Maxwell's treatise, he pretended the microscopic was like the macroscopic. And then everyone after the fact, after they didn't have experimental data on cosmology yet, they assumed, Einstein and them, they just wanted this flat, very boring universe that's very static, but we're not finding that. And so since they were hoping for that static universe, they made everything microscopic, when in reality, we need to think about macroscopic materials. So when you do this, you can get this notion of an index of refraction, because the transverse electromagnetic waves, which is light, they can travel at different speeds. If you've ever put a straw in water, you see that the straw gets bent, and that is because of the index of refraction of water in comparison to air. And the light is traveling at a different speed, so it affects how we visualize that. And basically, there's different types of exotic electromagnetic effects that can happen. Some of them to note, far fields only contain these transverse electromagnetic waves, which contain these 2 polarization states. And but we also have to consider near fields. And plasma physics also looks into these sort of noisy, out of phase modes that might be longitudinal, and they don't get into the radiation zone, but they are there in the near zone. So there are these third modes that exist, and also superconductors provide an effective mass to the photon inside the material, which is it's turning on this third mode. So I don't know, maybe Maxwell was onto something when he said there's 3 types of electromagnetic energy. Anyway, so now when we look into the macroscopic electrodynamics of materials, I'm going to suppress all of the vectors. So really, the electric field is a vector that points in 3 dimensions, but I'm going to simplify everything for this talk. So there's an electric field, E, and a magnetic field, B. And in vacuum, they have these epsilon naught and mu naught, which are the permittivity and permeability of free space. And these constants relate to the speed of light, which is a constant in vacuum. But in materials, as I said, this speed can change. And what is happening is that there is actually more than the electric and magnetic field in this macroscopic formulation. There's this notion of dielectricity and magnetism, which you can think of the dielectricity as essentially the electric field with adding in this polarization effect. So if you've seen, certain types of metals can get polarized, and like iron filings and stuff like that. So you can see that you can have materials that get this polarization that is in addition to the electric field, but it's only inside the material. And so this dielectricity is important to characterize those effects. And so instead of this epsilon naught, you get this epsilon, which describes the proportionality of the dielectricity to the electric field. And a similar story happens for the magnetic field. You get this notion of H, this type of magnetism, which includes this magnetization M, and that goes into B. So in vacuum, we have epsilon equals epsilon naught and mu equals mu naught, which implies that P and M equals 0. And these quantities they're in the equation for the index of refraction. So the speed of light in materials ends up using these epsilon and mu instead of the epsilon naught and mu naught. And you basically take the ratio here of the speed of light in vacuum to the speed of light in material to get the index of refraction. And I have to say, for the metamaterial story, it's much more complicated than this. Really, these epsilon and mu's are tensors, 4 tensors, and they're relativistic. It gets a little complicated, but if you're already doing general relativity, it's not that bad. So basically, we have these different materials, and you can have different regions. So most materials, epsilon and mu, you can look at this ratio. So if you look at the ratio of epsilon over epsilon naught, we can define this dimensionless quantity epsilon r. And we can do the same thing for mu. So most materials, they're around 1 for this epsilon r and mu r. So they're going to be above 0. But there are these different phases that you can have. And when you have both below 0 or one or the other below 0, you get more exotic types of materials. So we're going to need to keep this in mind. So we have some very interesting materials to look at. We're trying to get anti-gravity. So we need some minus signs somewhere. So before we get into metamaterials, I thought of this very vague analogy. So imagine you live in the United States. You always drive on the right side of the road, right? You just assume everything always moves on the right side of the road. So you kind of build your framework of thinking based on that. Locally, everyone always moves in that direction. And so you can make up these things. It seems obvious. No one can ever drive on the left side of the road. Why would anyone do that, right? It's not the way the laws work, right? Well, you travel across the sea and you realize that in some small locations of the globe, some phase space of all possible materials that exist in the universe, right? You realize that, oh, maybe in the UK or Australia, they actually drive on the left side of the road. And that's kind of what is happening with these metamaterials. You can kind of think of there being some region of space-time where everything kind of tends to flow backwards than the way you would traditionally think. And it's really not, I don't know, you can think of it as negative energy. It's not really negative energy. It's more effective negative energy. So these metamaterials, in general, metamaterials are designed to have specific engineering properties, for whatever application you're interested in. So this negative index of refraction is what we're going to be interested in. And basically, you can think of these different regions. So if you had vacuum and then you have this metamaterial, you can think of there being this energetic domain wall. And this picture matches nicely with some of the conformal gravity way of thinking. It's like you get these regions that are kind of separate, embedded in space-time, and the energy flows differently. So from the outside, it almost appears like it's a point, but really it's taking up a volume. And so it's not really negative energy, because when you're inside, to you, there's no negative energy. It's not like there's anti-gravity for you, right? In your world, in your bubble, there's no anti-gravity. Outside, there's no anti-gravity, but there's effective anti-gravity from the frustration of the boundary, from the transition, the boundary conditions going from the vacuum to the metamaterial. So that's why it's not as paradoxical as a lot of people might think. And you can kind of think about invisibility cloaking, because this stuff, metamaterials have been used for cloaking, and that bends light around. And, that's halfway there, maybe not even halfway there, but that's kind of the sort of idea. If you're cloaked, all of the light just bends around. And what we want to do is that rather than for light alone, we want to do that for everything that has energy, for the entire gravitational sector, such that everything tends to want to bend around it. It would be energetically favored to do that. So rather than, we don't want a rocket that's going to fight against wind resistance. We want to create something that prefers energetically for it to not participate in the gravitational fields. And so you can imagine inflating and shearing space-time in exotic ways, such that energy would tend to want to flow around it. That's the way I think about it, at least. So my next spotlight is Jack Sarfati, and David Kaiser, who's a physics historian, has called him one of the hippies who saved physics. So he's thought about some of these crazy ideas, such as time travel, but he actually has some serious mathematics to back up a lot of what he says. So that's why I've focused on him. And he's been the one to really point out that the Alcubierre drive alone is not efficient. It requires too much of this negative energy. We need to do something to get over this problem. And we need to recognize that these metamaterials and looking at macroscopic electrodynamics allows for this variable speed of light. And he might not exactly describe it the way I'm about to describe it, but this is how I kind of made sense of it and internalized it for myself. Basically, the speed of gravitational waves is the same as the speed of light. Everything that is massless moves at the speed of light. So when we say the speed of light, it's technically a misnomer. It's really the speed of massless particles, which includes light and includes gravitons, which is gravitational waves, right? So if we affect the speed of light, we have to keep in mind that for macroscopic general relativity, that is going to affect gravitational waves as well, right? So think historically what happened. What I said, Maxwell wanted to have his macroscopic theory for everything, and everyone decided to do this microscopic formulation. That was formalized, and then general relativity was established based off inspiration off the microscopic formulation. But now we need to go to study macroscopic materials. So we need to revisit macroscopic electrodynamics and understand how to generalize general relativity into the macroscopic materials framework, because we understand that gravitational waves are just massless particles, just like photons. So basically, Jack's idea is that pumped metamaterials, there's this idea of Froelich pumping, hope I'm pronouncing his name right, could lead to these types of exotic effects. So I'm going to show just a brief progression of Jack's ideas. So we're going to start with Einstein's field equations. Once again, we have the curvature on the left-hand side of the equation. Think of this as being some coupling constant in between. We have the Newton's gravitational constant up here and the speed of light. And we have the energy momentum tensor. This is where all the matter is coming in and sourcing the curvature. And then the curvature then tells matter how to move as a fictitious force. And so now when we go into simple materials, you could imagine this c to the fourth getting some correction factor from the fact that it's really like a v to the fourth now, because we're not, all the gravitational waves inside the material do not move at the speed of light anymore if we had some material. And it doesn't even need to be too exotic, even just water, right? So it'd be interesting. What if we put LIGO in water? If we made an underwater LIGO, we could actually, the way they calculate those signals, they have to triangulate everything. They have to use the speed of light to calculate that. So we could actually build a LIGO in water and detect if this happens or not. So it's not some crazy idea. It's something that is connected to reality. And basically, we can take this a step further by, this is really Jack's area of expertise, but I've followed it enough where basically once we start getting these metamaterials, that's going to introduce more complications than just the scalar S. That's where we're going to have to really consider these tensor quantities that I was talking about for the permittivity and stuff like that. So what you can end up doing, obviously this is a little bit of a simplification because I'm not telling you what this phi variable is, but you can think about going into complex analysis. It's very common to think about Fourier analysis and embed things into a complex plane where I is an imaginary number that is the square root of -1. And then we relate all the physics to the real quantity. So we put this quantity in the complex plane, we have some E naught, and then we have some complex phase, where the real part is giving us some magnitude times some cosine, right? And so if you've done a little bit of electrical engineering, maybe you've seen stuff like this before. And this same type of thing is what Jack is doing here. So we get these absolute values going in here, because really what we have to do is recognize that this TAB it contains the source from the electromagnetic energy as well. So really this S and this C to the fourth and the V and the T, they're all integrated together, they're all related. So when you go into the details of it, you plug in what the actual energy momentum tensor is for electromagnetism is, you can eventually solve for these variables and put it in this simple form. And this way we can get this cosine that's going to oscillate, and that's going to give us the ability to have negative energy density. And then the idea is that you want to pump with the appropriate frequencies such that you can get basically the speed of light. It's too large, so you want to make it slower. Actually, it's ironic. You'd think that if you want to move really fast efficiently, you want to break over the speed of light. So, oh, maybe you want to make the speed of light bigger, but that actually makes the problem worse. You want to make the speed of light smaller. So then it makes your coupling to curvature becomes more manageable. So obviously there's still a lot of great progress that needs to be done with the theoretical analysis here, but this is at least a concrete, simple theoretical understanding of how to get realistic antigravity based on general relativity and simply thinking about material science. And so once again, I'll just go through how I think about this analogy. Basically, we can think about how light is bent in water. And in special relativity, all massless particles move at the speed of light. So gravitational waves move at this speed as well. It's really the speed of massless particles. Therefore, gravitational waves should travel slower or faster in materials, depending on the material properties. So really this c to the fourth, sorry, when we go to the macroscopic formulation, we want to think about v to the fourth. And then if v decreases, we can get more curvature for the same matter. And then if we can get some minus sign coming out somewhere through the effects of the metamaterials, then we can get the antigravitic effects. Really, we're going to need the pumping, so it's going to oscillate between positive and negative. And that's going to be how maybe we could get to increase efficiencies. But obviously, there's still a lot of work that needs to be done because it's a very difficult barrier to get over. So, I'm not going to go into details. This is almost the end of my talk. And basically, the metamaterials that we might be interested in are stuff that has very small scale structure, things that are nano engineered. And one idea is something like quantum dots, which you could design it to have some maybe like self-similar structure at different scales. There seems to be exotic effects happening there. And I want to point out that conformal gravity has this scale invariance associated with it. So that's why I was trying to relate the conformal gravity to the metamaterials, because some of these metamaterials have this scale invariance. So if you were to study the mathematics of unified field theory, you're immediately getting into potentially applications for antigravity there. So basically some tools that might be useful rather than Fourier analysis, there's this notion of scale-dependent wavelength analysis, and this is complicated mathematics. So if we had some engineers that were computationally adept, maybe that's something they could try to learn, or something like this. So I think that's pretty much the end of my talk. So if I went through a little fast, I can definitely take some questions and things of that nature. So I guess I'll pause at this point and ask if, I'll first of all, thank everyone for attending. And second of all, if anyone has any questions, feel free to ask.
Well, David, it's Tim. So before we do anything, let me put it on gallery view. And again, I'm not going to unmute everybody, but I want to thank you. That was an absolutely tremendous presentation. And so thank you very, very, very much.